So this tutorial is mostly about negative dependence. So let me just define what I mean by negative dependence. What we'll have is, so we'll only talk about discrete measures. So we'll have a discrete probability measures. So that means we have n random variables, binary random variables, xi, or equivalently, we have n items, and we are seeing random subsets of these items. So the xi variables are just the indicator variables. So if item I is present, then xi is 1. So these are our binary variables. Now, what is negative dependence? So as a simple example, think that this random subset that you're seeing is maybe the subset of items that a customer buys on a given day online. So now there's different items that they could choose from and different items where they will actually click yes. Now, which items they buy is actually not completely independent. For example, if you know that they are buying a cell phone, it's very unlikely that they're going to buy another cell phone on the same day. So basically, the probability of seeing both cell phones jointly is smaller than if they were independent. So this is essentially what this inequality says here, that P of seeing both items together is smaller than P of seeing one item times P of seeing the other item. And by dividing by the probability of that blue phone, we can easily see that this really says that given that I know that I'm seeing the blue phone, it's much less likely that I'm seeing the other phone as well. So that is a fairly intuitive concept. This is negative dependence, negative correlation. Where does it show up in machine learning? Let me just give you an intuition, and Suvrit will later talk about in more detail about several different applications in machine learning. The first one we already see. Basically, any time we have something like a budget or so, where we know that a person will only pick a limited number out of some choice, that already gives us some kind of negative dependence because you cannot choose everything at the same time. More broadly speaking, anytime we have some prior knowledge that there's going to be diversity in our subsets that we are choosing. So this could happen, for example, if we want to do a recommender systems and we don't want to recommend the same or redundant items to people. We want to actually sort of cover a lot of different items that we recommend. Another example is firing of neurons, where we know we have a refractory period and the neuron fires, and then they can't fire for some time until they fire again. So there's like a distance between them, so there's diversity between the firings. Other examples are in computer vision, if you know that objects are not located in the same place, so they have to be spaced apart. This diversity notion also, or prior on diversity that you're implementing in probabilistic modeling, it can also help interpretability of your model. So you could think of that you want to model your data via clusters or latent features. And if you enforce that your latent features or clusters are actually really different from each other, they are diverse, what you can end up with is actually first more compact representations, and the second thing is that they may be also more interpretable and more capture actually latent groups in your variables, in your data. But there's more to negative dependence where it shows up, not only in probabilistic modeling, but also in randomized algorithms. So if you think about having a large amount of data, or you have very large models and you want to compress them somehow. One way to do this compression is to select a subset of items from this data or model and use that to represent the full set. And of course, at this point, you want these to be non-redundant. You want them to somehow capture all the information that you have. Hence, you want diversity or repulsion between these items. And one example is in matrix factorization. If you have a matrix and you want to approximate it by selecting a few columns of that matrix, you want these columns to really span the column space of the matrix. Another application is if you want to compress deep models and want to compress them by actually pruning neurons. The third area, big area where negative dependence shows up is when you try to do exploration, active learning, experimental design. Essentially everywhere you try to select some queries, experiments that you want to run or labels that you want to obtain before you observe them. You want to get as much information as possible. You will necessarily somehow spread them out. You will somehow want them to capture as different information as possible that's useful for you, to not have redundancy. So negative dependence has also shown up in many works where you try to do hyperparameter optimization, where you try to do experimental design, where you try to do Bayesian optimization, and so on. So we see there's actually a good number of reasons to look at the property of negative dependence because it occurs in many places in machine learning too. So what is up with negative dependence? Here's an outline of the tutorial for the next 2 hours, what we'll actually look at with respect to negative dependence. So we start with the introduction. We already saw a few examples. I want to show you one concrete example that's maybe the best known in the machine learning community, and these are determinantal point processes. And then we'll talk about not only negative dependence, but stronger notions of negative dependence and why they actually could matter and what nice implications they may have. And at that point, we will also look at relations between discrete probability and negative dependence and the geometry of polynomials as a powerful tool to reason with such distributions. And as a specific implication, I will then talk about how all of this can actually help you to sample from negatively dependent distributions. After that, we'll have a break, and then we will continue with part 2. And Suvrit will present some further implications. For example, how can you use negative dependence to approximate partition functions, which is typically a very hard problem. And then we'll talk a little bit about how you can actually learn a specific example, determinantal point processes, and in particular, many different applications in matrix approximation, in experimental design, and several other. And then we'll show you just some perspectives and wrap up. So, yeah, I don't know why. OK, it's back. OK, so this is the outline. Let's start with the first example, and let's look at one concrete distribution, determinantal point processes. So as I said, you want negative dependence that somehow captures some notion of repulsion or diversity. Seeing one item makes it less likely to see some other items. And one distribution that very intuitively captures diversity is the following. Think of my little example with the items that you can shop. And think every item is represented as a vector, some feature vector. And now the probability of seeing 2 items jointly is proportional to the volume that is spanned by their feature vectors. So it's just the volume of the parallelepiped spanned by those vectors, and it's actually proportional to the square. So now if you think about it, if you have items that are very different, this is going to be very large. If you have items that are very similar, this volume is going to shrink and shrink. And if it's actually the same vector, it's going to be volume 0, so you'll never, ever sample the same item twice. So this is essentially what this is represented here. And this notion of the volumes, you can generalize it to more than 2 dimensions. It's a bit harder to draw. So in 3 dimensions, it's going to be a cube, and so on. So you see directly, this distribution directly tries to essentially sample vectors that are as orthogonal to each other as possible, so somehow pointing in different directions, giving you different information. You can scale this also by scaling the lengths of the vectors. That is another possibility to introduce a bias towards certain variables. OK, so now the nice thing is that this notion of volume actually can be very comfortably and compactly described in closed form by determinants of matrices. All that you really need to define is an inner product between all your items or some similarity matrix equivalently. So what we really need, if we have n different items, we need an n by n similarity or kernel matrix where the ij's entry tells you what is the similarity between item I and j, or the inner product between the vectors representing those items. And this matrix should be positive semi-definite. And now I say that the probability of seeing Zs is proportional to the determinant of a submatrix of this big matrix. So to illustrate this, let's say I want to look at the probability of the set 2, 3, 4. I just take the rows and columns of 2, 3, 4, and that gives me a submatrix of my matrix indicated by these items, and I'll take the determinant of that. That's why it's called determinantal point process. So now we already see here, OK, I say proportional to the determinant. So the first challenge typically here is, what is the normalization constant here? What is the partition function? And in general, for discrete distributions, this can be very, very hard to compute. Luckily here, this is actually very simple to compute, and it's just in closed form. And in fact, many other things that are often hard to compute, like computing marginal distribution, conditioning, all of these are very easy with determinantal point processes. Essentially, they all have some determinantal formula where you do some simple modification to your matrix. So this is actually very nice. We get closed form formulas, and defining the matrix is something that we very often do in machine learning too. In kernel learning, you need kernel-based learning, you need exactly the same thing. All you need is feature vectors or similarities. A little bit to the history. So determinantal point processes, as far as I know, were first introduced in a paper by Odile Marquis in 1975, where they were called fermion processes and were actually modeling repulsion of particles. The name determinantal point process came up a bit later in a paper by Borodin and Olshansky. And I only have time to speak a little bit about these DPPs here. If you want to know more, there's actually a very nice survey by Alex Kulesa and Ben Tasker in the Foundations and Trends series that gives you a nice further introduction and also several applications. But let's look at a few examples where actually determinantal point processes show up naturally. So they show up in mathematics a lot. So for example, eigenvalues of certain random matrices have a determinantal distribution. There's also many combinatorial examples. Let me just show you two of those. The first one is an example of random spanning trees. So here, think about that the set of items that you're choosing from are the set of edges in a graph. And now what you observe is a subset of edges, and these subsets will always form a spanning tree in the graph. So you never have any cycles, and it's basically the largest set of edges that doesn't form a cycle. And now every spanning tree has the same probability. So you have a uniform distribution over spanning trees that can be described by a determinantal point process. And that is a very specific one because you will always observe sets of the same size. All the spanning trees have the same size, exactly m minus 1 if you have m nodes. It's not generally the case in determinantal point processes that you always observe sets of the same size. So this is a special one. The next one is a sense in random sequences. So here what I did is I just drew random digits between 0 and 9 and for every location here. So I get some random sequence of numbers, and then I mark every position where the sequence increases. So you get an increase from 0 to 2, from 2 to 8, from 0 to 9, and so on. So this gives me a random set of locations. And now I can look at this set of locations. That's a subset of all possible locations. And that can also be described by a determinantal point process. Those are just some fun combinatorial examples to show you. There's many more to show you sort of the breadth of this kind of distribution where all negative dependence shows up. What you can also do is you can just see, okay, what do these samples actually look like if I just sample them in 2D? So here I didn't take inner products. I used the Gaussian kernel. And on the left-hand side, you see samples of a determinantal point process. On the right-hand side, you see the same number of points sampled uniformly at random. While both of them somehow are very well spread out, the DPP is somehow better spread out. It really tries to cover everything, and the points are more repulsed. There's less clustering happening that happens still with the uniform distribution. So this just illustrates that really what the samples that you get are really, really well spread out in some sense because of the repulsive properties. And this already also is useful to model certain phenomena in nature. So here's one example. These are termite mounds in Brazil. This is a recent paper in biology just to show you. And they actually, so all of these black dots here are locations of these mounds. And you see actually that they are also very well spread out. So this is just another interesting example where possibly DPPs could be a very good model to describe natural phenomena. Okay, so now we know a little bit about determinantal point processes. I didn't tell you much where they are actually useful in machine learning, and you'll see many other examples of that later on. And in fact, many of the examples I showed you in the beginning, that's actually where you can use determinantal point processes, or DPPs. Let's instead look a little bit more into the theory, and let's look at kind of how could we actually more carefully define negative dependence, and why would we actually want to do that. And that's how we will come across the relation of distributions and polynomials. So here's just a reminder slide of my definition of negative dependence. So we have these binary variables xi, or equivalently random sets. And we say that the joint probability is smaller than the product of if they were the items were independent. So this notion of negative dependence is equivalent to the following inequality. It's essentially a negative correlation inequality, that the expectation of the product of the variables is smaller than the product of the expectations. Now, this already gives you a few different useful things, but often what people are after is maybe stronger things, like can we actually sample from such distributions? And this doesn't necessarily imply anything strong here. Or what about concentration results and such things? And for this matter, you could look at stronger versions of this kind of inequality. How could we make this stronger? There's essentially a few different things we could do. One thing we could do is we could say we could actually apply arbitrary functions to my xi and to my xj. And after applying these functions, the variable should still be negatively correlated. So that's stronger than just saying like this correlation inequality should hold. The other thing we could do is we could say, let's not just look at pairs, let's look at larger sets of variables. And they should also be negatively correlated. And we can do both of them. And the way we could do both of them is that we partition our universe into two parts. And now we take one set from each, like basically look at the intersection of S with one set and the intersection of S with the other part, and then apply some arbitrary functions. So that basically replaces the xi and the xj, the two different variables. And formally what this looks like is what is called negative association. So here I take the same negative correlation inequality, but instead of just taking xi and xj, I take a subset from I and a subset of j. So xi and xj are just like single pieces here, indicator variables. And you get out from this one, you get out exactly the same inequalities at the top. If you say the function g is the indicator function of item I, so it's 1 as long as item I is in my set, and h is 1 as long as item j is in my set. So these are two specific functions. The other thing that we need is that these functions are both monotone increasing. That means if my sets increase, the functions actually also increase. Otherwise, you could, of course, like if you put a negative sign, these things don't hold anymore. So this is the notion of negative association. It has somewhat of a history. It is known, for example, for people who are analyzing algorithms, they looked at this and its properties. It seems like this a little bit unwieldy to be like prove something like this, because it has to hold for all possible increasing functions, so it seems a bit unwieldy. So let's think a little bit about how we could actually like establish that this kind of thing holds. But before we do this, let me show you a simple example of a distribution where this actually holds. So it's again a choice type of distribution. So let's say we have a thirsty researcher, has time to go to one coffee shop, and there's a number of like k different coffee shops. And we have indicator variables, so bi is 1 if the researcher goes to coffee shop I. And now the set of bi's, of my bi random variables, is negatively associated. This is not so hard to prove if you think about the inequality with the indicator. So here only 1 will ever be 1. You can generalize this and say I go to one coffee shop and one lunch place and maybe one dinner place. So I have like 3 different groups of choices, and I pick one from each that also will have negative association. So what is up with negative association? How do I establish it? That's a stronger notion. And to think about this, let's first look at the counterpart, positive association. So for positive association, I could just take my inequality and flip it around and say instead of negative correlation, I have positive correlations now after applying my functions. And this is what you will get. So now we can do away with the disjoint sets, because a function is always positively correlated with itself. It's okay. That works here too. So this is positive association. Positive association also has been studied quite a bit, and there's actually a fairly well-known theorem that establishes a condition that implies positive association, and that is simpler to check. And this theorem is called the FKG theorem. after its discoverers, Fortuyn, Castellane, and Ginibre. And what this condition says is that if I take the probability of any set S times the probability of any set T is smaller than probability of their union times the probability of their intersection. This is also called the FKG lattice condition, or multivariate totally positive. So things like Ising models with positive correlation satisfy this. Certain Gaussian distributions satisfy this, several others. And the nice thing is that this condition implies positive association, and this is way easier to check. So since this is a well-known theorem, and this is kind of nice and has been used in many different places, we could say, well, what about negative dependence? Could we just flip both inequalities and get like, I can flip the lower inequality and say that always implies the upper inequality, like the negative association. Unfortunately, it doesn't work. So negative dependence is a bit more brittle and a bit trickier in this respect. So this is just one example where it doesn't, like the positive result, which is kind of nice, doesn't directly translate into the negative world. So what happens for negative dependence is that the upper guy implies the lower guy, but not vice versa. So we don't always get like exact symmetry. So what happened was, like, people looked at this and like, negative dependence is somehow a bit more tricky than positive dependence. So maybe also negative association per se is not the right notion of a strong notion of negative dependence. Maybe what we want is actually something else. So in 2000, Pimentel wrote a paper which was called Towards the Theory of Negative Dependence, where he surveyed a lot of different notions of negative dependence that were proposed or had been looked at, and said, like, what are the relations between those two, and what would actually be something that would be a good notion of negative dependence, and what is good. So he basically laid out a few different properties that this kind of notion should have. So one is that it should imply negative association. So we still want to have the negative association. And another one that is pretty natural is that they should be closed under operations that I do. So if a function has this notion of negative dependence, then its marginals should also have this notion of negative dependence. And if I do conditioning, I still want this negative dependence to hold. So I want closeness under all these things. And then there were a few other things like unimodal rank sequences. So rank sequence means that I look at the probabilities of each of the cardinalities of my sets. And this gives me like a 1 for 1, size 2, size 3, and I look like how do they behave as a function of the size, k. And this should be unimodal, and in fact it should satisfy something much stronger, so a stronger notion of log concavity. And this is intimately related actually to negative dependence. Another one is stochastic coverage that implies certain concentration of measure results. I'm not going to go more into detail of that. So these conditions that he laid out, that question was answered in 2009, and the key to answering many of his questions was looking at the generating polynomial of a distribution. So what is the generating polynomial? For any discrete distribution, I can define a polynomial by making the probabilities the coefficients in this polynomial. So now, if I have n items or n random variables, I get a vector of length n, that's z, and now I define a polynomial on that z. And that polynomial, I can take any possible subset of the coordinates zi, and the coordinates where I take a subset s will get the coefficient mu of s, so the mass of s, probability of s. So this polynomial I can always define, and it turns out this polynomial is actually key to many of those results. But let's first try to understand this polynomial a little better. So to get you a simple example, let's say we have two random variables and we define it on two variables. So here's what it looks like. You just get 4 terms. You can either have the empty set, item 1, item 2, or both of them. And here I just simplified notation by using a subscript. Instead of actually writing mu of empty set, I just mu subscript empty set. So this is the generating polynomial. Now the interesting thing is that operations I can do on this polynomial directly translate into operations I can do in my distribution and vice versa. And that can be very helpful. And to get you just a little bit of an idea how this works, let me show you 2 examples of this. So the first one is we just want to obtain a coefficient of this polynomial. So we want to pull out the probability of seeing just item 1. So this is mu of 1. How could we do this? So what we do is we first differentiate the polynomial with respect to z1. 1 is the item that we want. So since this polynomial actually has no higher powers, if you think about it, every z always occurs with power 1. All you have to do is you have to look at which terms have a z1, then delete the z1 and discard all the other terms. So what you get is mu1 plus mu12 times z2. And now what we wanted was to pull out the mu1. So what you just do is you set z in general to 0. So if you evaluate it at 0, and what you get magically is mu1. So this works also if you do something that's like larger sets. You just differentiate with all of the items in that set, and then you set z to 0, it'll pull you out exactly that coefficient. So that was example 1 that already shows you, okay, there's like some relation between those operations I can do and if I want to know something about my distribution. The second one I want to show you is marginalization. So let's define a new distribution over just one item, the first one. That's just the marginal of 1. So basically, what's the probability of seeing item 1 in my sets? How do I get the generating polynomial for that one? So what you do is you set z2 to 1. So basically, all the other guys you set to 1, all the ones corresponding to items not at 1. And then I just collect the terms. So what is remaining is just c1 as a variable. And if you look at the terms that you're getting, I just wrote them out here for you, is that the first part that doesn't have a coefficient is the one that's mu empty set plus mu2. And that's the probability of not seeing item 1. And the other part is the coefficient that actually remain with c1, and that's the probability of seeing item 1. So what I got here very easily by just setting some stuff to 1 was the generating polynomial for the marginal distribution of z1. That's just example 2. So this actually is fairly simple as an operation. And you can imagine that if I say, okay, there's like certain operations I can do on the polynomial and I get actually operations that work on the distribution, properties of the polynomial should also translate into properties of my distributions and vice versa. And that actually holds true. And the specific property that we will be after here is something that relates to the zeros of this polynomial. So where are actually which z's make this polynomial 0 or don't make it 0. And in a landmark paper in 2009, Borsea, Brandon, and Liget defined the distribution, this family of distributions called strongly Rayleigh measures. And these are defined actually exactly via these generating polynomials. And what they say is that this polynomial should satisfy what is called real stability. So what does that mean? Real means the coefficients are real numbers, which we get because their probability distribution has like real values of probabilities. The second, what does stable mean? Stable means that if the imaginary parts of the z, of all the zi's are positive, this polynomial shouldn't vanish. So none of the zeros should be in that part where all the zi's are positive. And it turns out this class of families actually satisfies pretty much all the conditions laid out by Pimentel, except for some conditionings. So this looks a bit weird to like this condition, like all the imaginary parts bigger than 0, sorry. To get a little bit of an intuition for it, if you imagine just a polynomial of one variable. If I say that if the imaginary part is bigger than 0, this shouldn't vanish, since the roots come in pairs, conjugate pairs, it means that the polynomial only has real numbers as roots. So it's a real rooted polynomial. And essentially what we have here is some generalization of a polynomial whose roots are only real. And these so-called multi-affine functions where you have only powers of one of the zi's give you such a generalization. So this is a generalization essentially of real rootedness. To give you even more of an intuition, if you look at what does this polynomial actually look like for a determinantal point process, for example, what you get is essentially a version of the characteristic polynomial. So characteristic polynomial, if you remember linear algebra, it's essentially a polynomial that tells you what are the eigenvalues of a matrix. And the matrix that we talk about here is that similarity matrix. And since it's symmetric and positive definite, this matrix has real eigenvalues, positive numbers. So the zeros of this polynomial will also be real numbers because of that. And now the other nice thing is that actually real stable polynomials have a very rich set of mathematics around them that we can use and translate to our distributions. So real stable polynomials have been studied quite a bit. Studying the univariate case actually goes back to at least Newton. So there's the so-called Newton identities. There's lots of interesting studies. In particular, people have identified powerful closeness properties of these polynomials. Basically, what kinds of operations can I do on my polynomial that retain the real stability property, that don't change that? And I could go ahead now and take these operations, as we saw operations on the polynomial, translate into operations of my distribution, and see what do they actually correspond to in the world of distributions. And that's how you get the results such as closeness under marginalization, closeness under conditioning, and so on. So it just follows from actually looking at the theory of these polynomials. Another thing I just want to mention is that the condition that my polynomial is real stable, this generating polynomial, is equivalent to this condition that I wrote here. And that is a condition that looks at derivatives. So what you do is you take any two items, I and j, and you first take derivative with respect to I, and then you take derivative with respect to j, and you multiply this, and then you do on the right-hand side what you do is you just take the polynomial, or you take twice, you differentiate twice. So product of differentials versus differencing twice. And what you should get is if you evaluate this at any vector x, that the left-hand side is larger than the right-hand side. So this looks a little bit counterintuitive. It implies actually things like this log submodularity or log negative lattice condition that I showed you with the positive correlation, positive correlations. And in fact, the way you get the lower identity is by actually differentiating with respect to all items in S and all items in T. If you remember, that's how you get out actually the coefficients. These are the distribution, like the probabilities. Another thing is that if you look at this condition, it looks also pretty alien, but if you actually look at this condition and look at different types of negative dependence people have looked at, they actually correspond to variations of this condition, such as this holding only not for all x in the reals, but maybe just on the positives, or just evaluated at 1, and so on. So actually negative dependence per se just means this condition should hold evaluated just at 1 and nothing else, so x equals 1. So this condition also shows you like how these different negative dependence properties become stronger and stronger. So we have the power of real stable polynomials, and we have this negative dependence properties it implies. What does it gain us? Let's look a little bit of the properties of strongly Rayleigh measures or SR measures. The first one is that actually I get these closeness conditions like closeness under marginalization, under conditioning, and several other things. Like multiplying with the independent distribution also keeps you in the class. So that is useful for many different things. The other thing is that this strongly Rayleighness implies many different of the negative dependence conditions that were proposed earlier. So negative association is one of them. There are several others you get out. So for example, this expectation of products is smaller than product of the expectation. These kinds of correlation inequalities. Other things that are useful is concentration of measure results. So if you have these strong negative dependencies, essentially your variables behave like as if they were independent. And that can be very useful. If you want to analyze dependent random variables, that's typically much harder than independent random variables. So where this has been used a lot is in algorithm design, where you do like dependent rounding or something, and you'll certainly have dependent variables, and you still want to show some kind of concentration inequalities. This is where this can be extremely useful, and often you actually get negative dependence there. So this has been established for like just looking at the sum or the expected like the cardinality of the sets. You can do it for Lipschitz functions and matrix inequalities too. As I already indicated, this gives you algorithmic implications. And one area that I'm going to talk about next is in terms of sampling. You will actually get fast sampling algorithms out. The second one that we'll talk about in the next part is to approximate counting, approximating partition functions via optimization. And the third one is approximation algorithms, as I already indicated, for example, to analyze randomized algorithms. So there's a lot of there's even more different things that you can do with these polynomials. These are two important ones where also there has been quite a bit of recent interest and work on those. So we get these nice properties, we get different applications, possible applications, and there's going to be many more in machine learning, I think. Let me show you one other strongly Rayleigh measure that is not a determinantal point process. So determinantal point process we kind of hand-wavily established by saying the polynomial is like the characteristic polynomial and eigenvalues are real. So this one looks like a determinantal point process, but is not. So here we have a huge matrix that has lots of columns and more columns than rows. And now the probability of selecting a subset of columns is proportional to the outer product of this determinant of the outer product of these columns. In a DPP, you would take the inner product. So this one is not a DPP, but it satisfies the strongly Rayleigh property. So the difference is also that this one actually you can sample more columns than if they are in dimension D, more than D columns, whereas if you take inner products, the matrix will always be low rank. So how do you establish that this thing has the strongly Rayleigh property? And in fact, how you can prove this is by using exactly the closeness properties of the polynomial. So you look at the generating polynomial and you can relate it to a polynomial that is related to a determinant. And so you start out from a real-rooted polynomial and you end up with one by doing these translations. So actually, you start with an SR polynomial and you end up with an SR polynomial. So this is again where the power of using the polynomials comes in and actually helps us establishing this condition. Another thing you may actually wonder is where does the name strongly Rayleigh actually come from? Where does this Rayleigh come from? And in fact, the Rayleigh comes from the so-called Rayleigh monotonicity property if you look at electrical circuits and look at how conductances behave. So this is essentially related to the Kirchhoff laws. And this actually people looked at when they were looking at random spanning tree type distributions. So this also says that, okay, our random spanning tree distribution from the beginning is a strongly Rayleigh measure. That's another example. However, there's also limits. So negative dependence is nice and powerful, but there's also limitations to it. For example, I told you that, well, negative dependence implies notions of diversity and repulsion. Maybe sometimes we would actually have sort of a handle on how negatively dependent things are, like how diverse things are, how much do they repulse each other. One way to do this would be to say I take actually my probability to a power p. This is almost like a temperature. So if p is 0, you get a uniform distribution. If p is 1, you get the original SR measure. If p is bigger than 1, you get like even stronger repulsion. So you get a graded version. Is this still a strongly Rayleigh measure if I take arbitrary powers of p? And unfortunately, it is not. So while this is a very useful thing to do, this is sort of where the strongly Rayleigh closeness breaks. You can still use this notion, and it's still going to be useful to you, but it's not directly strongly Rayleigh. The other one is certain types of conditioning. So another application that people have looked at was, well, I want to use maybe a determinantal point process for inducing diversity and for subsampling data, for example, for summarization. But I also want to have fairness at the same time. So my data is actually partitioned into different groups, and I want to ensure that I sample enough from each group. So I should not sample more than a certain budget from each of the groups. So if you enforce that constraint and condition on seeing only subsets that satisfy this constraint, you also get out of the strong Rayleigh class. So this type of conditioning also doesn't hold anymore. However, you can still get results for partition functions, for example. So after having seen a little bit of the theory and sort of the indication that maybe looking at analogies to polynomials, let's look at one concrete area where actually the strongly Rayleighness can be very useful, and that is sampling. How do we sample from negatively dependent measures? For many of the, like some of the instances, there's specific samplers that work exactly for like this type of subfamily of strongly Rayleigh measures, and one are determinantal point processes. And there's actually a very beautiful result saying that you can use the eigenvalues and eigenvectors of your similarity matrix to do sampling with determinantal point process. And the sampling works in two steps. First, you sample eigenvalues and essentially a subspace, and then you select points according to the subspace that you selected. However, this needs you to do an eigenvector decomposition. Or if you know your matrix factorizes as an A transpose A, then you need an SVD of A. If you actually know the factorization of your similarity matrix or the actual vectors representing your items, you can do a bit better. So for example, you can do what was also called dual representations for sampling. Based on this result, there have been numerous approaches to accelerate this sampling. In particular, many of them build on like reducing the complexity of the matrix L or the complexity of the matrix A. And you can do this with various different methods. You can do sketching methods on the matrix that somehow preserve volumes because that's what you care about. You can do Nystrom methods, you can do MCMC, or you can do other types of two-stage sampling where you first introduce core sets or do this via another type of DPP. Beyond that, there's other approaches, for example, doing reverse sampling, doing Kronecker, approximating a matrix with a Kronecker matrix, and so on, that also accelerate sampling. So there's been a lot of work, and all of these actually do give you good mileage in making the sampler faster. However, this works only for determinantal point processes because it explicitly uses the similarity matrix that we defined. So what about general strongly Rayleigh measures? They may not actually have that matrix with them. So one method that works for all strongly Rayleigh measures is MCMC sampling, Markov chain Monte Carlo. And the sampler here is actually fairly simple. So you start out with an initial set as 0, and then what you do is you uniformly at random pick one item inside the set and one item outside the set. So you pick item A inside and B outside, and then you do one out of three things. Either you try to swap them, meaning you kick A out of the set and you add B to the set, or you just add B, or you just remove A, or you do nothing. And you do any of these with a certain probability, and these probabilities essentially give, if they are defined right, they give you a sampler for the desired measure. So this is a very, very basic MCMC Markov chain. And you can do essentially the same chain if you actually want to condition on having only like the sets of the same cardinality. So that retains actually strongly Rayleighness. I could say, I want a distribution, but I only want sets of size k. What you do is then you start out with a set of size k and you only do the swaps. And you never do add or delete, which will change your cardinality. So it's essentially the same sampler. How does it work? So the one thing with MCMC is that it's kind of hard to know when it has converged or not. So let me just show you this empirically and theoretically. So empirically, what I'm showing you here is actually applying, in particular, determinantal point processes to matrix approximation. So we're sampling columns from a matrix. And what I use for the convergence here is actually the matrix approximation error. So this is already the application sort of down the line. And what you see with this is that actually pretty quickly the sampler converges to a pretty good approximation, and it basically stays there. So the convergence actually empirically works quite well. What about theoretically? And in particular, this was like measured error in like my application domain, like the actual approximation error of the matrix. So in theory, what we look at is what's called the mixing time. That means in my sampler, I started with an initial set, and then I do random modifications to my set. And after t steps, I have a distribution for each set. What is the probability of being at that set after t steps? So this gives me a distribution over my sets. And I want this distribution eventually to be essentially the mu of S that I want to sample from. That's when my sampler has converged. So what the mixing time looks at, what is the difference between this distribution after t steps and the distribution that I actually want. And I can do this in various divergences, for example, total variation. So for example, I could look at how many steps do I need from a given starting point, initial set S, until this is smaller than epsilon. In particular, I don't want this to necessarily be exponential time. So this question was first studied with respect to especially this negative dependence in combinatorics. So for a class of combinatorial objects called balanced matroids, where an important paper by Fedor and Mihail in 1992 established that this gives you fast mixing, meaning something that is essentially n times k times log of 1 over epsilon, where k is the size of the set. What is a matroid? I'm not going to give you the formal definition here. You can think of it as a combinatorial generalization of linear dependence in linear algebra. So basically what you have is a collection of subsets, and you are to have a uniform distribution over this collection. An example would be the spanning trees that we had. Or if you think of the example with the coffee shops, if I say I'm going to one coffee shop, one lunch place, and one dinner place, this would also be all the feasible sets would all have size 3, and that would also be a matroid. So a special class of these matroids are the so-called balanced matroids that exactly exhibit these negative dependence properties. So after this important paper, in 2016, Anari et al. Generalized this result to sample from determinantal point processes and more generally any strongly Rayleigh distribution if you condition on cardinality. So if I say I want a fixed cardinality k, then I can essentially generalize those combinatorial results to arbitrary strongly Rayleigh measures. And I get essentially the same kind of mixing time. In particular, it's log of 1 over epsilon. That's what we want. Now, what about arbitrary strongly Rayleigh measures where the sets can have arbitrary sizes? So in the same year, we generalized the result to hold for arbitrary strongly Rayleigh measures with exactly the Markov chain that I showed you. So basically just this simple pick an item inside, outside, and try to swap them. So it's actually very simple to implement it. Just for illustration, I want to give you an intuition. How do you actually prove this result? Because it uses, again, essentially the polynomials to prove something about the distribution. So how do you go from being able to sample k out of n to be able to sample any kind of subset out of n? And the idea is actually fairly simple. So what you do is you start out with your n items, that's your universe, and we duplicate that set. So we essentially create a shadow set, and then instead of sampling anything out of n, we sample n out of 2n. That's fixed number out of a fixed number. So this we can do under certain conditions. And then what we look at as our actual sample is only the selected items that fall on the left-hand side. And on the left-hand side, I can have anything between 0 and n, because I do n out of 2n. So we do n out of 2n. The only thing that I really have to define here now, and that's kind of the tricky thing, is what is the distribution on the other part, the shadow part? So this distribution has to satisfy two things. The first thing is that if I only look at my left-hand side, it better be the same distribution as I was starting out with. So basically the marginals on the left-hand side should be the correct ones. The second thing is that the joint distribution still should have this strongly Rayleigh property, because otherwise I don't necessarily can use the fast sampling results here. So those two need to hold. And the way you can define this kind of distribution is by using actually modifications of the generating polynomial. And especially the operation you use here, so-called symmetric homogenization. So to summarize what I told you about sampling is there's many specialized samplers for strong Rayleigh measures, but to have some like one global sampling result for strongly Rayleigh measures, we can use MCMC methods. And the proof at its core actually essentially reduces everything down to a negative correlation inequality. That's all it does. So basically it needs negative association to hold. So it needs this strong Rayleighness. So what we see from this is that we actually get, from negative dependence, we get fast sampling algorithms, generically, with a strong Rayleigh property. The second thing is that we can actually, especially for DPPs, we can accelerate that sampler further by accelerating each iteration of the sampler. So we know we need like not too many steps, so each step can now be further accelerated. The results on DPP sampling also generalize to some extent to continuous sampling for DPPs. I just want to mention that. And another thing I want to mention is that strongly Rayleigh is sufficient for fast mixing in Markov chains. It's not sufficient. So there's some very recent work showing that actually if you have what is called complete log concavity or strongly log concave distributions, they also give you fast sampling, and it's a broader class. The results are a little bit trickier. But yeah, this is some interesting new work. Finally, going even broader, there has been also several recent works on sampling from log submodular distributions, meaning just satisfying this lattice condition, the weaker one that I introduced with positive dependence. So those results are mostly conditional or empirically. They don't generically give fast sampling, but there's also a lot of interesting recent work in this area. With this, I would like to just summarize. So we saw negative dependence comes up in various ways in machine learning. It actually gives you lots of beneficial properties. It's fairly easy to reason with if you know there's an interesting and very powerful and deep relation to the theory of polynomials. And this gives you algorithmic results, it gives you concentration results, and many other things. In particular, it gives you fast mixing Markov chains that you can do sampling fairly easily. So we'll now take a short break for about 10 minutes, until 12:05. After that, we'll talk more about specific applications and partition functions and several other powerful implications. Thank you.
You mentioned Ising models.
Yes.
Ising models with random.
start the tutorial. So the second part will be given by Silvestra. So
We got sniped.
Okay, welcome to the second part of the tutorial on negative dependence, stable polynomials, etc. So that's where we are. So first part, Stephanie just gave you introduction, some beautiful theoretical properties. I'm going to just talk about two simple theoretical questions of great value in practice before showing you some concrete applications. And my aim in showing you some simple theoretical stuff is just to gain some further insight about some of the power of this mathematical machinery that Stephanie just outlined here. And I will then just go through a diverse set of applications to just get your imagination going about what all other things you could do in machine learning with this. There's just some set of applications where I happen to have some more input on, hence I'm sharing those with you. It's just to stoke your imagination for all sorts of things you could do with this paradigm of thinking. And I will then exit after the applications by telling you some recent perspectives on, at least on the theory side, how things are expanding, while also outlining potentially some more broad level things for future outlook on this topic. And if any of you is particularly interested in purely direct, open questions in the area, try to catch me, it means not right after the tutorial because I gotta eat, but at any other time during NIPS. So, okay, here we are. Flyby theory, just very simple stuff. I'm not going to go into the details because details are fascinating in themselves, but I just want to briefly expose you to some simple theoretical ideas. So what I'm going to talk about are just partition functions, which is basically the normalization constant of your probability distribution, and an particular algorithmic task that I happen to look at also. So just for definition, the job of computing a partition function, also known as the normalization constant of a distribution, is, so if mu was like the unnormalized measure, so in Stephanie's part there was a mu, you could think of it as, let's say, an unnormalized measure, some just non-negative function that you normalize over, of course, by summing over all possible subsets. There's 2 to the n of those. These things are typically, for the general discrete case, intractable. More broadly, this normalization constant, the way it occurs for maybe most familiar to people in machine learning, either within graphical models or within when doing Bayesian inference, where it comes as during posterior inference. So these are typically intractable quantities, and hence one devotes a lot of energy trying to approximate them, get around them in one way or the other. And of course, the reason I'm mentioning this here is that, quite interestingly, once again, this beautiful property of negative dependence in stable polynomials helps you come up with powerful approximation algorithms to approximate these otherwise intractable looking quantities. Partial hope, just from this potentially only exception, means there are sort of minor twists of this exception that exist in the strongly Rayleigh land, but morally they are pretty close to this exception that nature makes. But just to get an insight that, hey, there is some hope for partition functions, if you were looking at a determinantal point process, then the partition function is just the sum of those determinants over all subsets. Whoa, it happens to have that awesome closed form formula. That's a rare thing, okay? But still, it's pretty amazing. And this beauty is behind many of the nice things one ends up being able to do with DPPs. Similar luxury, of course, does not hold for general SR measures or the exponentiated version of SR measures that Stephanie had mentioned. But that doesn't mean we stop and give up, because it seems something special is happening for determinants. Okay, it's mostly linear algebra, but actually these SR measures, they have several properties intimately in common with the determinantal ones, so maybe one can do something. And the answer is yes, in fact you can. And I'm not going to tell the details, but of course this is a tutorial, so I just want to expose you to the right keywords, and Google can educate you after that. And of course some key concepts so that you can also put the search results in context when you search for them. By using properties of stable polynomials, these crazy looking quantities can be approximated within a constant factor. Of course, it's e to the n, exponential. It's not so bad because remember Stephanie made analogy of these with like log submodular. So if you were to take log of stuff, that n in the e to the n would come downstairs. And without exploiting the stable property, it's not easy to get such an approximation. So it's a pretty awesome deterministic approximation. I'll give you a concrete example also, okay, so that you can appreciate it slightly in greater detail. But the key behind this is actually a brilliant piece of work done by Leonid Gurwitz in 2006. He kind of changed the way, or he brought the stable polynomials more into mainstream, because he came up with a new proof of an 80-year-old conjecture by applying the machinery of stable polynomials in a very creative manner. And his motivation was to approximate partition functions, essentially. That's what was happening. I'll show you that precisely. Just like I said, it's a view in flyby view. It ends up trying to take the approximation problem. So that approximation problem of computing the partition function is related to trying to find the minimization of this polynomial over that product of all z's being positive. Now, positive zi, you can just replace it with e to the yi, right? And what you end up getting, because of the property of real stability, is that this is actually a convex optimization problem. It's in fact what people call geometric program. So he takes that intractable problem, comes up with a convex relaxation, which intimately uses the stability property, and then he's able to prove some properties about the convex relaxation, how from that he can recover an approximation. So here is a concrete example. It's a theoretical example, but it kind of hopefully gets the point across to you a little bit. So an object that has greatly intrigued people who swing this way is matrix permanent, and it is used to count the number of perfect matchings in a bipartite graph. So in some sense, in the simplest setting, partition function can also be thought of solving a counting problem. How many such objects are there? So it's a friend of the determinant. In case somebody, I hope everybody has at least heard of the permanent. If not, here it is in your face. If the summation had an alternating character there, like -1 to the power of sigma, it would be the determinant. That thing ends up having a closed form formula. You replace the alternating signs of these products with just a +1, poof, it becomes hard to compute. I mean, not so surprising, but that's what has fascinated a variety of people in a variety of areas, and it still fascinates people, including me. So this was Leonid Gurwitz's idea. Permanents approximating this quantity, which seems to have n factorial terms. So you're not going to, of course, compute n factorial terms via the magic of stable polynomials. And what he does is, this is that property of repeated differentiation that Stephanie said. Differentiate enough number of times to extract the coefficient of your desire. So Gurwitz's idea was, write down that polynomial down there, product over those of linear terms. Each of those linear terms is a stable polynomial, clearly linear and hence stable there. Product of stable polynomials is stable, so that whole product is stable. If you differentiate it n times, set whatever junk remains to 0, the coefficient that you can extract is the permanent. So that's a very clever way to write a permanent. But the fact that he could now write the permanent by repeated differentiation of a stable polynomial, and we know that if you start with a stable polynomial, repeated differentiation keeps you stable, is making a very strong statement about how these coefficients can behave. So in some sense, in the whole business of stable polynomials, the fact that the roots are positive gives you a very strong number of implicit constraints on what the coefficients can be. And those strong implicit constraints end up implying then strong things about the permanent, because that happens to be just a coefficient in that stable polynomial. And in particular, that's the kind of inequality he proved, which as a byproduct solves a famous conjecture, but it basically then establishes a machinery for analyzing several difficult-looking combinatorial objects by coming up with a nice convex relaxation. And this idea, Griffiths likes to call the right-hand side optimization problem the argument of the infimum as the capacity. That has been used by many people by now, mostly in theoretical computer science. And it really intimately exploits the stability property. So this was just an illustration of how these tools can help you get a handle on some otherwise very hard-looking quantities. I'll mention an open problem for the interested people in the room. Permanents count perfect matchings in bipartite graphs. If you wanted to count the number of perfect matchings in a general graph, nobody yet knows how to use this machinery correctly for that. Because in particular, you can't apply the stable polynomial machinery anymore. But still, you can do some kind of interesting convex relaxation. Nobody yet knows how to analyze that. So in case you care about that, just an aside. I may throw in some other such asides if I have time. Okay, that was just a flyby. Let's do another flyby before I talk about some other concrete applications, because I want to kind of speak to everybody here. So a task that all of us in machine learning care about is learning stuff from data, right? And so the version with which we started a few years ago is, okay, fine, this DPP, this probability measure is parameterized by that kernel matrix L. Where does it come from? The age-old problem, right? So, and of course in machine learning, that's the standard answer we have. If you don't have something that you need, learn it. So you learn it from data. A broader question, this is again a kind of aside to keep in mind, is to think about how might we go about formulating the task of learning these other SR measures. They were too general. Maybe you can discover some nice parameterized class and learn that. But anyhow, all of that has to be motivated by the right application. But if you're also curious mathematically, you can do that nevertheless. So of course, our application was, once we learned this parameterized model, then we can sample according to it, and then use those samples in a subset selection problem or in a recommender system or something. So I'll come back to that. And in fact, this type of learning was motivated and studied by Kulesa and Taskar back in 2011. Then later, others have also studied it and published in this conference or in ICML, setting up a variety of different formulations of the learning task as an optimization problem. I will set up the simplest such formulation. So here is a simple formulation for you. I observe, somehow or the other, n different subsets, capital N, of a ground set of n items, little n, sorry, two different n's in there. And I just want to get a maximum, I just set up some kind of maximum likelihood estimation problem. So I just want to learn parameters which are kind of maximize this log of sum of the log of the probabilities of having observed, assuming that these observations were indeed coming from a DPP. Even if they don't, you can still solve this problem, right? Nobody's stopping you. So that's what the optimization problem looks like. That optimization problem is non-convex. Maybe it's, I think it's hard to solve, but it has been studied in greater detail, and so much more is understood about it by now. I'll mention those references soon. So here is a simple looking optimization problem. One way to solve it is by this amazingly simple algorithm discovered by my student Zelda Marier a few years ago. Here is this amazingly simple algorithm. So you start with some L, run this iteration. Then you scratch your head. Of course, you don't discover it like that, but I can present it like that, right? And then you scratch your head to see, does this actually lead to a solution? It's actually a very interesting task to try to verify that this simple iteration is implementable, as you can see, in 2 lines of MATLAB, actually works. It's a pretty decent algorithm for solving locally, for solving that maximum likelihood problem. And in fact, to this date, we don't know if the second term, so this looks like some kind of fancified gradient ascent method. If the second term you add a step size in there, it still works, but we don't know how to prove that. But anyhow, that's an aside. There is recent work on just the MLE problem. So for studying asymptotic properties of MLEs for DPPs, it's done by those authors. I think Victor might be in the audience. I don't know if he's here. And learning a DPP via methods of moments, again, to optimize sample complexity, that's also has been studied recently. So there's quite a bit of interesting theory that has been developed for the MLE problem, though in the, let's say, statistical version of it. So when you look at this, many of the large-scale people in the room may say, well, you have those matrices and you have these gradients of determinants. Those are not easy objects to compute. What should I do? So, of course, the basic iteration, if you implement that, costs n cubed. How do you get around that? Paper 1, paper 2, paper 3. I mean, you can do all of them in one paper if you want, but you can also do it separately. But what that means is you make some sacrifices to the model, right? And then you can scale up. So one of those is the KDPP, where you restrict to only sample subsets of size exactly k. Then the progress, then the iteration can be sped up, but not this iteration, but then the learning task can be simplified by looking for a smaller class of DPPs, including a low rank version. Like you can try out all these ideas. So either exactly k is the support, or less than equal to k is the support, or there is another version. You write L as a Kronecker product, so support can be of any size, but because it's Kronecker product, you can scale up, amongst many other ideas. But the point is, learning task, which has downstream applications, becomes interesting enough to discover a variety of different techniques to scale it up. And I may comment on this later, but I think recently people have also started trying to learn these kernel matrices by embedding them within some nonlinear feature learning framework, like a deep model or something. Okay, so some open problems for you. Just broad problems, okay? It's not specified super sharply. So one problem is just learning parameterized classes of other SR measures of interest. Efficiently learning this exponentiated or sharper version of power DPP. So it has algebraically, it still has determinants, but now it has a power. The reason it's hard is we can no longer easily compute its partition function. We can approximate it, but not easily compute it, so the learning task becomes more challenging. Or just learning that temperature parameter to have just a single scalar to interpolate between uniform sampling and sharper until as p goes to infinity, you come to the mode of the distribution. And so on. So there's a variety of open problems worth studying further, including you don't have to just go via the MLE route, you can come up with some other learning framework, including like a GAN style framework or a negative mining based framework, etc. Okay, so that was flyby theory plus algorithm. Now let me just, in the remaining time before I have to wrap up to tell you some of the perspectives, try to quickly go through as many of these applications as possible. So, and what we'll do is, I think, to kind of streamline the rest of the speech, after I'm done speaking, then I can handle questions. Right now, maybe I can just go like a train. Okay, so the first one, actually, I learned of this recently, even though this has been classically the common motivating application for diverse sampling, the idea of recommending a diverse subset within a recommender system, kind of diversity was recognized around 2001. In recommender systems in machine learning, it's more recent. That was a joke, by the way. And it's a big topic in recommender systems to diversify the basket of stuff shown to users, right? Twitter still doesn't do a good job. It shows me the tweets from the same person 10 times, come on. So they need to do this. So recommender systems, however, there's a bunch of challenges, you know, like you want to recommend, you can see I just picked up some channel for babies and children's songs or something. I don't know, if you look at the subtitle, it doesn't look like that diverse, even though the pictures look quite diverse. So you can already see, depending on what features you're using for your kernels, notion of diversity starts to become quite challenging to engineer, right? So anyhow, so there is a very interesting work coming out actually pretty recently, is how to handle diversified recommendations in real life. So this is coming from some people at Google, to try to use a DPP to essentially more fine-tune the feed or interesting videos to watch that YouTube could show you. And this application raises the motivation of this paper, exposes the user to a sort of very cool challenges that arise when trying to do diversity in a real life production type environment. For instance, we never talk about this, but the moment you try to do a real application, this is the first place things fail, right? The model's notion of diversity may or may not have anything to do with a user's notion of diversity, and different users may have different notions of diversity. What are you going to do? Tough problem, right? So anyhow, all those problems do raise new questions on how to do negative dependence, but nevertheless valuable to identify them. How to scale this to large-scale data? Fine, means Google may have gazillions of computers, but when we are experimenting, we may not have those computers. So it's, even they may need those computers because data comes in every day. How to scale? A more interesting challenge which makes it sometimes harder to adopt more sophisticated models is how do you integrate this more powerful sophisticated model in an existing ecosystem? They have a full engineering stack where gazillions of features are coming in, being engineered, cleaned, generated, whatnot. Finally, something is ready to be recommended. So at which stage can you plug in a negatively dependent model to do diversification? That's then production level decision, a very crucial one. So the way this paper handled that decision is they say, okay, let us learn the deep learning based features, etc., etc. We'll use those nonlinear features, and only in the end, out of the 100 identified items, rather than rank them point-wise, one by one I show you, this is the best ranked video for you, second best, I'll select a subset of diverse videos. So rather than point-wise, I operate set-wise, and to go from points to sets, they use DPPs. That's kind of the summary, but it's, you can see how much more work goes into translating something into reality, but it's really nice that they can do that. And it's a starting point. There's many other interesting applied plus theoretical open problems that arise as a consequence of this work. Okay, so that was one. Let's do the flyby of the next application. This one is, let's say, a more theoretical and simultaneously practical application, is the famous Nystrom approximation. So many of you may have heard something like, I don't know, random kitchen sink, random Fourier features, Nystrom approximation. So random features say, okay, let's not look really at the data and just do some random features. Matrix approximation, low rank matrix approximation, Nystrom approximation, these methods say, let's actually look at the data and try to come up with a more data-driven approximation to a kernel matrix. So if I have a kernel matrix, it's a big box of numbers. I want to approximate it with something that uses fewer parameters. I don't want to have n square in there. For n data points, I'll have an n square kernel matrix, n square entries. Each entry takes some time to compute. I want to approximate it with something smaller. Well, low rank approximation, but what low rank approximation? Stephanie already hinted at this, but actually this particular task, people in our community have studied since a long time. So Nystrom studied it, I think, in 1930 when he was doing quadrature, but it was taken up in machine learning earliest by this Williams and Zager paper from 2001. Their motivation that time was to scale up Gaussian process regression and inference with GPs, another consumer of kernels. And there's been a variety of ideas on how to subsample data to come up with a good approximation to the kernel matrix. And the fact that I'm talking about this, you can guess, I'm trying to pick columns. It's a symmetric matrix, so you pick rows, columns, same thing, right? So I'm trying to pick columns of this matrix to come up with some kind of low rank approximation. And by the theory of talks, because I'm talking about it, clearly these columns will be picked according to some SR style measure, nothing other than our friend the DPP. So in fact, what I'll do is I'll pick a subset of columns according to a KDPP. I should have called it a CDPP because I want to pick C columns bigger than equal to K, but whatever. And I'll construct this approximation, K hat. MATLAB notation. Sorry to the Python folks. So fine, but interestingly, you can subsample according to that dependent probability measure, and you can prove that it's not too far from the best rank K approximation, which actually SVD or eigenvectors would give you. And it has some further downstream implications on regression, that if you were to, if you were doing kernel regression, instead of using K, you would use K hat, how the expected risk behaves. So it's pretty interesting that one can prove something like this because these are non-IID samples. And of course, I wouldn't share this with you here unless these things actually also work in practice, because remember, we are talking about applications. So in fact, if you try to have this dual axis scatter plot, x-axis is the time it takes to generate the approximation, y-axis gives the quality of approximation, how much is the error, then clearly you want to be closer to the origin. There's a variety of choices based on either cluster the data, k-means, or do some leverage scores or adaptive leverage scores or so on. And when engineered correctly, which means if you implement the sampler nicely, then a DPP-based approximation is kind of getting you best of both worlds. So there's running code for this. So this is a reasonable approach, which of course can be further improved, but let me not go there. This was an interesting application. It's just a starting point to get people thinking in this direction. Okay, this is just a proof of concept application. This is motivated by the following idea. You have a big model, you want to compress it without losing the model's predictive power. What are you going to do? So those of you who work in neural networks or compressing neural networks, You may be aware of a variety of heuristics to do this, right? People like to do this. It's an important thing. Anytime you have, say, a big model you trained on some cluster with 1,000 GPUs, now you want to compress this model so you can deploy it if you want, a version of it on your small hardware, like this thing, unless you assume internet access. So how would you go about model compression without losing capability? Well, it means maybe my model is parameterized in a way that I can do a dependent sampling of the most diverse parameters, subselect those, reallocate and then delete the rest while doing some adjustment because I'm deleting and damaging the model. Might this simple-minded thinking work? And interestingly, we tried it on just here's a toy kind of setup, feed-forward neural network. You take a layer, you see, oh, these neurons, they, of course, they co-adapt a lot. Many of them, they look repetitive. So some of them, they do learn different things, but many of them do learn redundant things because these things are almost always over-parameterized. So can we delete some of the redundant ones? Challenge is which ones? So even though I say, okay, fine, again, by theory of tutorials, I'm going to say some SR measure or some determinantal measure, but which one, right? Can you learn that measure differentiably? Would be great. So once you start putting these things into an application, of course, all those concerns are important. But suppose we pick some simple parameterized probability measure which allows us to do this negatively dependent sampling, and we tune that or learn it from data. This is a supervised task here. Sample according to that. So this is done in a work called diversity networks that we had worked on a couple of years ago, which does exactly what I said. And it had this interesting property that, hey, if I were to just randomly delete, then it takes, I have a lot of, this is test error, okay, not training error, because ultimately in machine learning, that's what we really care about. And if I do some kind of importance-based pruning, okay, I can do better than random, but if I actually do carefully engineered diversity-based pruning, I can compress the model by taking a much less severe hit on the prediction performance. So this is just a proof of concept of how to go about compressing a big model. And I invite you to be creative about coming up with other settings and scenarios where you could profit from compressing models. So one other small application, then I'll spend some more time on a slightly bigger application. This is just us trying to see what else kind of correlates with diversity and what are some of the challenges that arise from that. Well, sometimes trying to be overly biased towards diversity, please, this is all in the context of math here only, nothing with the rest of the stuff. You may tend to actually pick outliers because they will look maximally different. I mean, that's the very definition. It's a vague term, right? Outlier is as good as fine-grained a mathematical term as diversity, whatever that means, right? So then you may flip it on its head and say, fine, then in that case, we could use some tuned measures of diversity to help do outlier detection. Just another application that seems natural. So in fact, here I'm talking about using that diversity measure where I have this temperature parameter, p equal to 0 is uniform, and as p grows bigger, p equal to 1 is DPP, p bigger than 1 is something stronger than DPP. The preference for picking outliers will change accordingly. So p is equal to half looks like this picture, and as you compare visually, p equal to 1, you can see the bias towards outliers, p equal to 2, and stronger bias, and so on. So in particular, this is one example of using those stronger notions of negative dependence. Even though this is not an SR measure in general, if you're just doing outlier detection within that application, it seems to fit quite well. And it works fairly well. It has some very interesting mathematical properties which I don't have time to go into, but for those you should consult Zelda. Okay, I think the last application I want to talk with, because this also branches out to establishing connections to other areas that many of you may be familiar with, is this application to optimal design and active learning. So I just stole this picture from Itiha, from the ISE group. The kind of motivation is experiments are expensive to run. So one simplified version of this you can think in language of supervised learning. For many real problems, getting labels is very hard and expensive. But even if we could get the labels from an expert, so this is not like mechanical Turk style labels, these are like actual labels. Running the experiment itself could be hard because this involves doing something in a wet lab. You're trying to figure out something about a biological process, a chemical process. You have a limited budget, so you can only carry out few experiments. Then as you're running the experiment, you're kind of uncertain about whether your model is explaining what you're observing. So you want to decrease your model uncertainty. And how might you decrease the model uncertainty? By figuring out what would be the next best experiment to run, and so on. So that kind of is an entire sub-area called optimal design of experiments. You can have a Bayesian approach to it. You can have an online learning, active, whichever way you want to think about it. I'm just talking about one very simplistic setting, which I will describe in precise detail in the next slide. Is this particular motivation? Experiments are expensive to run. I'm using some fixed model. My model has uncertainty, and I want to reduce my uncertainty by picking the right set of experiments to run. What does this translate into formal language as? This is the translation. So suppose I have m possible experiments that I can run, and each experiment involves these measurements. These are vectors, let's say n-dimensional vectors, and there is scalar outcomes. So just to get the model across to you, let's assume the trivial linear model. The labels or whatever regression values here are given by a linear function of the measurements. And the aim, one way of formulating this experimental design problem of picking optimal subset of experiments, this is just one way, not the only way. It's just for illustration, but it's a very widely used formulation, is to pick a subset of, say, size less than equal to k, or say k is your budget, of which experiments to run to minimize uncertainty. So now you look at the covariance matrix inverse there, and you can see it is indexed by I belonging to S. So it's like the covariance of the experiments that you choose to run. So the uncertainty is characterized, the amount of uncertainty in there is given by that inverse. And you want to minimize the uncertainty. So you want to, what do you want to do? Like that thing is a matrix. So what is that phi function? Phi function is just something that takes that uncertainty matrix, spits out a single scalar for you so that you can understand some single number on what quantifies uncertainty. And we want to minimize the uncertainty. So you have a budget. So this is, as you can see, it looks like a combinatorial optimization problem. It's developed in great detail. If you care, there's a classical reference text on it by Pukelsheim called Optimal Design of Experiments that outlines a pretty nice story around this whole topic. So in case you're interested further, check that book out. It was recently reprinted by Siam. So here it is simultaneously. So if that scalarization function, that's what I'll call it, if you take it to be the trace of that matrix, you get what is called A optimal design. My guess is for average. If you take D to be the determinant, you get what is called D optimal design. Both of these are combinatorial optimization problems, by the way. And recently, Also, yeah, I don't have all the citations here due to shortage of space, so if somebody thinks I missed anything, please let me know. But these are some recent works that have considered coming up with approximation algorithms with guarantees for solving these problems. So for A optimal, there is that set of authors, and the D optimal version has also been viewed as an application of general theory developed by other authors. And those are the two most widely known ones. Interestingly, if you, instead of trace or determinant, you pick some other coefficient of the characteristic polynomial of a matrix, also known as this coefficient is also known as an elementary symmetric polynomial, you can interpolate between the two extremes of A optimal and D optimal. But the crux is that this is a combinatorial optimization problem, and there's a full set of them that you can solve. But the most interesting consequence here of negative dependence is that you can use some kind of greedy algorithm here to pick which experiments to run, and you can prove how well does that greedy method perform. And the proof of that depends on, so not the implementation, the proof of it depends on being able to sample according to this probability measure, which we call dual volume sampling, which, as Stephanie noted, is not a DPP, but it's an SR measure. And some of its value for experimental design actually was outlined in this paper by Avron and Boutsidis in 2013. We looked at the generalization of that theory to elementary symmetric polynomials, and authors in this room like Dersinski and Wormuth, they came up with a clever procedure to sample very efficiently according to this measure. We also looked at sampling from that by just invoking an MCMC procedure. And there's quite a bit of interesting follow-up work from some of the authors on this topic. So this turns out, this measure is okay, it turns out to be negatively dependent, SR, etc., valuable for experimental design, but and hence it has several implications for regression, but it also turns out to have several other interesting properties that people have recently investigated. So now I've kind of shared with you a diverse subset of applications of diversity. So that kind of is the end of the diversity and stable polynomial story. So in the remaining time, let me just try to quickly wrap up by telling you one quick aside for enthusiasts and aficionados in the room, and then a quick wrap up, okay? So here's a quick, super fast, this one will be fast. So the dual of the D-optimal design problem is also known as the minimum volume covering ellipsoid problem, which is one of the most fundamental geometric problems in convex optimization. Okay, it comes up in the analysis of theory of interior point methods also. There's a nice monograph written by Michael Todd on that, published in 2016. Essentially, it ends up looking like this, max log det of blah. So it's a convex relaxation. Objective is concave here. So here we see that, wow, there was optimal design, then it was connected to stable polynomials, and somehow then there's a convex relaxation of a combinatorial problem which connects to deep stuff in geometry and optimization. So doing that with more general than D-optimal is an interesting stuff that you could think about. This is for the aficionados. Okay, so there's a bunch of other ML applications, no time to talk about those. I listed few. Some of the broader version of these things you would see, of course, within log submodularity. There's been a bunch of tutorials on that. The idea of diversity people have been exploring now in reinforcement learning, because you want to explore nicely, not always exploit, so diversity becomes important. Same as, this is what Stephanie had mentioned, within fairness in machine learning, or summarizing videos, you want to extract a subset of frames to summarize a video without being redundant while being meaningful, and so on. So I will, when I update the website, there's a website corresponding to this tutorial. The website will actually have links, clickable links for you guys there, in case anybody wants to follow up later and chase the references, okay? this bunch of work, I searched, maybe I hope I didn't miss anything. If I did, please let me know, I can update my slides. There's a bunch of related, diversity related, not necessarily stable polynomial, but diversity related papers at this conference. And there's actually several of those. I'm not going to speak one by one through this, it's just slide is there. My slides will be online soon, so you can get this anyways, unless if you didn't take a picture yet. So let's try to wrap up now after all of that. We talked a lot about these stable polynomials and their applications and some of their generalizations, some theories and whatnot. There has been some recent progress, recent as in as of November, so pretty recent progress, that I thought I'll share with you in this tutorial. So it's leaving the world of negative dependence a little bit, but not fully. Stephanie hinted at that. So there is actually, once again, our friend Gurwitz introduced in 2009 a class of polynomials which he called strongly log concave polynomials. So he introduced first stable polynomials to partition function estimation. Then he said, wow, stable polynomials help me estimate partition functions. Are they the only polynomials that help me estimate partition functions? You could have asked that question also, right? So he asked that question and he came up with a class of polynomials to help him estimate partition functions of more complicated probability measures, and he calls those strongly log concave polynomials. It's actually a pretty impressive set of things that one can do with that. And recently, these polynomials, their properties were further developed by some authors, Anari Garan Vincent, who actually then developed further properties of these SLC polynomials and used those to solve some long-standing conjectures in combinatorics, including something of direct value for us, including giving a concrete example of a larger class of polynomials where you can get fast mixing Markov chain Monte Carlo without always requiring the SR property. Of course, you lose a few things when you go out of stable polynomial land. Your constants may worsen, you may have less precise rates, you may have less precise things to say, but at least you can say something rather than nothing. And in particular, for the fractional version, the exponentiated version of SR measures, as long as the fraction is smaller than 1, you actually, even though you leave SR land, you remain in the SLC land. So something works out. This is just super fast because this is very recent stuff. Don't have time to go into that. Of course, whether it will have applications at all in machine learning leaves to be seen to the creativity of the audience here. Okay, so I already spoke that, so let me not re-speak that summary. Let me conclude with an outlook and then I will stop. So the outlook is here. Hey, it went away. I did too much animation. Oops. Let me bring it back because that sucks. So here is the outlook. I hinted at this, but there's a beautiful number of deeper connections to the world of optimization that stable polynomials enjoy. Uncovering those connections for people who care about optimization, like me, is an important to do. Modeling diversity, I mentioned to you from that recommender system example that fine, a model has some notion of diversity, but a user or sets of users, different people may have different notions of diversity. So how should we go about modeling diversity? Just like there is a lot of enthusiasm in the community currently for modeling fairness, similarly, I think the time is right to talk about how do we model diversity. And I hinted at, okay, SLC does something for MCMC, but can one cook up a comprehensive theory of sampling and approximation, which is richer than just the story I told you today? And beyond that, as application suggests, you cannot always bias yourself to either just negative dependence or just positive dependence. can we come up with a graded and controlled manner on how to model and mix and use efficiently both positive and negative dependence in our applications and, of course, in our math. So those are like some rough outlook directions. And I think with that, I will stop and thank the two students whose work contributed a lot to both Stephanie and my shares of the work on this topic. Thank you.
Thank you. So it's time for questions. If you have questions, please come to the two microphones and stand in line.
Hi. Is it on? Is this on? Yeah, okay. Thanks for a great tutorial. This is new to me and this was awesome. So I don't know if I made a mistake, but can this be extended also to continuous spaces?
So excellent question. So as people continue to go out, so he's asking, can we talk about these distributions over continuous spaces? And yeah, the answer is yes. You just need some more care.
I see.
Yeah.
And do you see any...
There's also extensions not only to sets, but to multi-sets. So yes, extensions are possible.
Okay.
But, and some people have studied those also.
Can you put that reference up also in the tutorial?
Okay.
Yeah. And also my second question is, do you see potentials in thinking about non-convex optimization? Because I can intuitively think that in some sense diversity could help to...
I see. So I think the other question probably, let me guess, it's coming from this idea that in non-convex optimization, how could diversity help in non-convex optimization? Yeah. One answer is already there in some of the references. I cite people who are doing Bayesian optimization to do global optimization of black box functions. They choose to explore the space using diversity to explore it better and hence attain a better solution. So yes, there is already some proof of concept.
I see.
Now,
The
if you
discrete
open the
case.
black box and you use gradients and subgradients, whatnot, then what can you do? Remains to be seen, but there is potential. Definitely.
I see. And that's in the discrete case, that reference?
I think the batch Bayesian optimization is also discrete.
Okay.
Hi. That was a great talk. Really enjoyed it. I'm afraid I'm not much of an expert, so I apologize if this question is naive. But this is with application to the things you were talking about with respect to reinforcement learning. So there, the field seems to have started to settle on a notion of diversity based around maximum entropy, where if you want to visit diverse trajectories through state space, you should maximize the entropy of your policy. And I was wondering how the things you've been talking about relate to that formulation.
So the question again, hopefully people heard that, okay, in reinforcement learning, people are maybe quantifying diversity using entropy and maybe sometimes distances and so on. How would probability measure relate? So one thing I would say is that that's why I kind of ended by saying we need to establish more formally what we even mean by diversity. Okay, entropy kind of does that for you by saying, okay, how uniform are you? And the less uniform you are. But one benefit about having this graded or controllable model of diversity is that you could learn it for your task. Rather than fixing a prior and then just hammering away, you could learn this from data. And it could be used with or as in combination with or as a replacement of entropy-based thinking, but again, it depends on the application. Yeah.
Thank you.
Hello. I want to make it aware that this optimization problem you mentioned at the end, this issue to maximally sample something, we applied Polya's enumeration theorem to build a large enough group to do that, to study AML risk. And we'd love to get your opinion on it on Friday when we talk at the AI workshop for challenges and opportunities in financial crime.
Okay, great. Cool.
Quick question. So you mentioned that the DPP idea can be used to simplify a deep neural network. You also mentioned that to train the DPP, you can use it using gradient descent. Have you thought about like connecting the paradigm of DPP, because it's a log determinant, making it actually deep and use gradient descent to train for the deep objective?
So there is some paper in a workshop here on Friday or Saturday, which talks about deep determinantal point processes, where they jointly kind of learn deep features in combination with logdat. But if you mean something more beyond that, then I don't know.
Yeah, maybe in terms of the objective.
Okay, yeah, it is possible, because in the end everything is differentiable.
Right.
So the challenge is how to be scalable, because determinants are not easy creatures. So one has to make some sacrifices to gain scalability.
Thank you.
Okay, I close the session now. Well, and you can ask the question in front. So let's thank the speakers again.